Okay, here we go. Now we are going to begin a lesson on the input and output circuitry inside the PLC. And it's important that we understand this. We understand how we're protected and what is actually happening internally inside the PLC for a compact PLC like what we're using in this particular course, or inside a input or output card of a PLC. We have some objectives. We want to be able to describe the input from the field and how it is detected inside the PLC. We want to explain how those inputs are protected inside the PLC. We want to describe how an output to the field is sent from the PLC, and we want to know what is actually happening internally inside either the PLC itself or the output card. We want to list the types of input voltages that are allowed in our particular unit that we're using for this course, the Micrologix 1100, and also the types of output voltages that are allowed for this compact version of a PLC called the Micrologix 1100. Okay, so let's look at the circuitry, and what I am going to go through here is a theoretical explanation of what's happening. We physically don't have these components inside. I'm trying to relate the current unit that we're in to the previous unit when we were hardwiring all our controls using relays and motor starters. Now I'm trying to just relate that to what's going on inside the PLC. I'm going to show you a theoretical explanation, and then I'm going to show you the physical circuitry in the next slide. So don't think that, okay, I have an 8-pin relay for each input inside my PLC. I'm just trying to show this to kind of tie the two units together here. Okay, so first we have some sort of control voltage that we're going to receive from the field, and from the previous lesson we learned that we're going to wire that to an input, and the inputs are on the top on our Micrologix 1100. And so the very first input is I/0, and if we sense control voltage. Now in our particular unit, we're going to learn this in just a few minutes. All of our inputs are going to be direct current for the inputs, and they're going to be 24 volts. That's our particular model. There are other models that will accept other voltages, but for the particular model that we're using here, they're all going to be 24 volts. So when I say control voltage, on our model that will mean 24 volts, but it could mean a different voltage type and magnitude for a different model. Okay, so generically we're just going to call that control voltage. We're either going to have either the absence or the presence of control voltage on these inputs because they're discrete inputs. Remember, discrete means that it has two states, on or off. So we in this case are going to have a input that is on. It's sending control voltage, and in our case that would be 24 volts into that screw terminal. That means that I would have current running through that particular circuitry for that particular channel, and internally it would energize a coil. Now physically it's actually not a coil. We're going to look at the actual circuitry here in just a moment, but I'm just trying to again theoretically show you what is happening internally. And what is happening is much like in manual motor controls, we're energizing a coil with that 24 volts. Well, what happens when we energize a coil on a relay? We close internal contacts. Those internal contacts are what we're going to actually use inside the PLC. Now, if you remember from the lesson on relays, that there is actually no electrical connection between that coil and that closed set of contacts. And what we're going to learn, the actual circuitry for this, there's actually going to be no electrical connection between the sensing circuit and the circuit internal to the PLC as well. Okay, so when those contacts close, that means that address is going to evaluate to true inside our instruction set. If we're examining for a closed set of contacts, we're going to have a lesson on these instructions next, but the particular instruction that I'm showing right here is called an examine if closed. And so in this case, it would evaluate to true because we said that those contacts would close. Okay? So that's just kind of a theoretical explanation of what is happening on each one of these inputs. Is we have a theoretical internal coil that we're energizing, and when that coil gets energized, we're closing a set of contacts. Those two are electrically separated from one another, and then we can use instruction sets to test that to see if it's closed or whether it is open. Let's look at the actual circuitry now. And before I wanted to put up some electronic circuit, just wanted to explain theoretically what's happening. So the PLC inputs are protected from outside interference and noise using this particular circuit that I'm going to show you. And the protection of this circuit is on the input, in our case, the input that is natively on our compact PLC, or it could be on an input card if we're talking about a modular PLC configuration. The protection is termed Optical Isolation, and that's going to make sense here in just a minute. But opto meaning optic or visible light, and isolation meaning we're electrically isolating the physical input from the circuitry inside our component, the PLC. And there are no physical electrical connections between that field device and the PLC. That's why we use this optical isolation, and it is to physically protect from something actually causing significant damage inside our PLC. So you can imagine out in the field we have a lot of different voltages, high voltage, a lot of dangerous things that could come across our input wiring, and we wouldn't want to bring in 600 volts, say, into this little compact PLC. That could do a lot of damage, or it could, do bodily harm to personnel. So what I have here on the right-hand side is actually a circuit that is used internally, and there's a couple components there that we really didn't study in electrical applications, but a quick explanation will help you understand what's going on here. First, we have our 24-volt DC power supply, and that's just the power supply that's on your panel. So that black unit that is on our panel that supplies 24 volts is going to be used to power up all of our field devices, just like we did in manual motor controls. And then we have input devices. Now, we're showing a set of contacts there, but that could be a limit switch. It could be a float switch, normally open or normally closed, pressure switch, selector switch, any type of input that you want to have there. And of course, since it's a discrete input, discrete meaning it has two states, it can only either be of the normally open variety or the normally closed variety. Those are the only two options because it's a discrete input. Now, if you notice, those are outside the dotted box, meaning that that's out into the field. The dotted box is actually showing our opto isolation circuit. So inside that circuit, there's a couple symbols there that are probably new to you. The first one you probably know quite well, just because of LED bulbs, LED displays, those sorts of things. LED stands for light emitting diode. So if you look at just this little symbol right here, the downward triangle with the perpendicular line, that is a diode. The two arrows that are pointing in a 45-degree angle down are showing that light is being emitted from this diode. And that's where we get the term light emitting diode. So that diode, when it is energized, will glow. And what happens is it will have a glow to it when it's energized. And this right here is a photosensitive transistor. And a transistor, in its simplest description, is just a switch. When something happens here on this little stem, this is going to let current flow through here. If we don't have some sort of activating event here on that little stem, and a lot of times that's actually voltage coming in, In this case, it's a photosensitive transistor, so if light is coming in at that little stem, this is going to be for all intents and purposes, a closed switch. So when the light comes on, that switch is closed. When the light goes off, the switch is open. You can think about it that simply. We really didn't study transistors in first semester, but that's in all practical purposes, that's how it works. Now, if we have current flowing through here, that means that we are going to have a voltage drop across this resistor. Well, the voltage drop, we only have one resistor in this entire series circuit here. So that means this total voltage, whatever it is, VCC just stands for source voltage, and inside the PLC it's 5 volts. That 5 volts will be completely dropped across here, and then that will be sensed inside the PLC as a true input. So that is how we can isolate the actual input from the internal circuitry inside the PLC, because it is used, the medium to pass the value between the two is light. And so light is not going to emit any electrical charge across that bridge, and so we're optically isolated. So the main thing that I want students to understand is the way that we protect inputs is through optical isolation, and optical isolation has no electrical connection from the field to the internal circuitry of the PLC, and it does it through the use of light. Okay, so it's those three main components. We're protected through optical isolation. Optical isolation separates any electricity from the field from electricity that is being used inside the PLC, and we do that isolation through means of light. Okay, and I'm showing here the last bubble. I forgot to pop it up. Is the PLC input is now evaluated to true. Okay, so let's look at our output circuitry now, and our output circuitry operates differently. It is quite a bit simpler, and so we'll go through that. In this simple program that I have here, we have one rung, and that rung has one test instruction. This right here is called a test instruction, and this is called a set instruction. Okay, so this is testing some sort of address that is held inside the PLC, and this is setting some sort of address held inside the PLC. Okay, so first thing we're going to do is we're going to test this address. That particular address was the one that we were just looking at, the very first address. Remember, we're 0 based, so we start counting at 0 and then count up to 9 in our particular case for 10 total inputs. We're testing that address of 0, and in this particular instruction, this is called an examine if closed. If you notice, if we had a normally open set of contacts, what are we waiting for it to do? We're waiting for it to close. So this is actually testing that address to see if it's closed. Well, a closed set of contacts sends 24 volts. And we stated earlier that 24 volts evaluates to a true statement. 0 volts evaluates to a false statement. So if this is closed and it is evaluating to true, then that means that we are going to send what we call logical continuity down this rung. And since there's no other decision made along there, it's going to send a true to this output address. So if that rung evaluates to true, there's only one instruction that did evaluate to true, so the rung evaluated to true, that internal coil will be set to true. Okay? If it is set to true, now again, this is a theoretical explanation, so I'm kind of showing you in terms of an 8-pin control relay, but this is internally what's happening is this coil here will be, quote, energized. And if that coil is energized, that means that these internal contacts will close. And if they close, that means whatever control voltage that we have wired into this input, we're going to talk about different voltages that we can wire in there. We're using direct current for the first 5 outputs, and then we're going to use alternating current for the 6th output. But in this case, we're going to take whatever control voltage that we have there, and we're going to send it, because this is closed now, we're going to send it out its neighboring port here, which is O/0, and that will send that whatever that control voltage is out to whatever field device that we have wired to that particular output, and it will energize that output, that control output. Okay. Let's look at this in its whole. We looked at the first input channel and the first output channel. Now let's look at all the channels together. Now it's kind of small to see here, but this is a depiction of that little opto isolation circuit copied multiple times here for each one of these inputs. Each input has its own circuit. And as we showed, the outputs are literally just contacts that are closing. So I have contacts that are closing between our voltage source and our output destination. So all the inputs on our Micrologix 1100 PLC are going to be direct current 24 volts. So we don't have to worry about mixing and matching different voltages in this particular case. Other model numbers will allow us to do other types of inputs, but for our intents and purposes, that's all we needed. So we will be using 24 volts DC on all of our inputs. All of our outputs are called dry contacts. What dry contacts are is contacts that close, but the PLC itself does not supply the voltage to them. We have to supply the voltage to them, and we're going to see that here in just a moment. So we must supply the voltage to each one of these. Now the presentation that I have here, it shows 24 volts going to all of these. This is how we did it prior. On the last channel, we're actually going to, on VDC for 05, we're actually going to be bringing in 120 volts alternating current, because that's where we're going to energize our solenoid valve out of. I wanted to add that to the curriculum just so you could see that not all outputs have to be equal with one another. So this is a little bit of an old slide, but we're going to have outputs 0 through 4 will be on 24 volts direct current, and then that 5th one will be 120 volts direct current. Okay. And here I'm just showing that they do not have to be the same. In fact, you could alternate them all over. You could have 30 volts DC for the first one, 24 volts AC for the second one, 120 volts. You get the gist. There's a myriad of different final control elements that we're controlling, and therefore there can be a myriad of different voltages that we have to send to them. Okay. Now here, let's look at the range and breadth of what we can do with these outputs from our PLC. So this is a table right out of the manual for our Micrologix 1100, and the maximum voltages that we can have is 240 volts AC, and these are make or break currents. I'll explain those a little bit more in a future lesson, but we could have up to 7.5 amps of a make current. In other words, when we close, the inrush current that we measured with our motor when we started the motor, we could have up to 7.5 amps. Now, if you remember, when we had our half-horse motor on 120 volts, our inrush current was higher than that. So we're definitely going to have to use some sort of interceding control device like an 8-pin control relay, and we will, to control the output of this, the output to that motor, because it would be too much inrush current for our little Micrologix PLC here. But if we had an inrush current lower than that, we could easily just skip the control relay and wired directly to our final control element. Okay, and here for our 120 volt or our direct currents, we could go all the way up to 125 volts DC. Of course, we're going to be way down at 24 volts. Now our inrush current is very low there. Over here, it actually talks about volt amperes, and volt amperes is literally the formula for how we can calculate, if we use a lower voltage, how much current that we could have go through. Well, if we're at 24 volts, we're going to be higher than an amp, because 24 volts times 1 amp would be 24 volt amperes. All of our devices are going to inrush current when we close them, because we're going to be using our control elements like our motor starters or our control relays. The inrush current is in the milliamps, so we're not going to be concerned with that. The only thing that we are really going to go directly to our final control element is our solenoid valve. Our solenoid valve operates off of 120 volts, which is our middle row here. And if you notice, our make current for 120 volts AC is 15 amps. I happen to know that the inrush current when we close that solenoid valve is something like 4 amps, and then the holding current for that is going to be it's less than an amp. So we are well within the bounds of our abilities to directly connect our solenoid valve to our PLC, so we will not be using an interceding control element like a control relay in our case, and we will be sending power directly to our solenoid valve in that case. So that concludes the lesson on input and output circuitry. So let's go through a little review here. Describe how an input from the field is detected within the PLC. So it is detected through some circuitry, that optical isolation. This is also going to answer our second question of how it's protected. But it is, we're going to supply 24 volts into an input channel, and that 24 volts is going to be isolated from our input circuitry inside the PLC through optical isolation using a light emitting diode that will react a photosensitive transistor. And since there is no electrical connection through that light connection, we are isolated from our input voltage. If we have 24 volts, we will have a true or logical true, and we will store a 1 in an input table saying that we have a true. And if we have 0 volts, we will have a logical false, and we're going to store a false inside our input table. The outputs are sent to the field from the PLC through just a set of dry contacts. Dry contacts are contacts that we have to supply the power that we want to send out to the field. So if you remember, we can send 120 volts on one channel, 24 volts on another channel, 30 volts on another channel. And they have dry contacts in them, so we're not just designating that all outputs have to be 120 volt outputs. So we can have AC or DC, on inputs. For input voltages, we can only have DC voltage, and can only be 24 volts. We have no options there. For our output voltages, we could have AC or DC. AC could be up to 250 volts, depending on the current. I said AC, right? AC is 250 volts. On DC, it's 125 volts. And of course, we have some limits on our current there as well. And we can look back at the table to see those different voltages. Okay, so that concludes our lesson on input and output voltages and circuitry. And so the next lesson, we'll actually get into the addressing and how to break down the address and be able to locate the address in a specific input or output table. So we'll see you next time.